Hello everybody and welcome to this new video in our series of videos in current electricity. So today we are going to be talking about voltage, Ohm's law, and EMF of a battery and internal resistance. Now let's look at voltage. Or some people call it potential difference. A short form of it is PD. Now in electricity we denote voltage capital V, and it is the work done per unit charge. It's actually the work done in moving a unit charge. Okay, so therefore means that the SI unit is joules per coulomb, because the SI unit of work done is joules and the SI unit of charge is coulomb, but usually we denote this as volts, capital V. So if somebody tells you I have 6 volts, what does it mean? It means that 6 joules of energy are required to move 6 coulomb worth of charge. Okay, now we can relate voltage and current with a simple circuit like this. So we have a battery here that will be giving us a voltage of, let's say, V, and the current that is delivered by this battery is capital I in this direction, and the resistance is R. Now Ohm's law tells us that V, that's the voltage of the battery, is the product of the current and the resistance. In other words, voltage is directly proportional to the current that is flowing across a resistor. So it means that if we plot a graph of current in amps against voltage in volts, we are going to have a straight line that's passing through the origin definitely, and whose gradient here is going to be representing the value of the resistance of the resistor, which is given in ohms. Now we're going to pay a close look at internal resistance of a battery and EMF. Batteries have internal resistance. Batteries are transducers that can generate electricity from chemical interactions in the battery, and the energy per coulomb that is produced by this battery is what we call the EMF of the battery. We call it EMF or electromotive force, and we denote it epsilon. Now here is the diagram that represents what's going on in the battery. We have a kind of small internal resistance associated with the voltage supplied by the battery, which is all inside the battery, and then we are going to have this sort of external circuit to which we have a resistance R and a current I that is leaving the battery in this manner. Okay, so we will definitely say that the EMF of the battery here is the current I times R, But it's not just R we're talking about here. We also have this small resistance that constitutes the internal resistance of a battery. So we're going to say that epsilon is R plus capital R plus small r. So it means that the EMF is IR plus I small r. This part here accounts for the loss of energy, because it's just like an energy that is lost, and this accounts for the battery being warm when it is functioning. So therefore we can deduce from this the useful voltage, which some books are going to call the terminal PD, or the terminal voltage, which is this here IR, or we can just say that it's equal to V. It is the EMF of the battery minus I small r. So how can we then determine the internal resistance small r of the battery? Now I want you to notice that we cannot measure this voltage loss directly, so we are going to use experimental methods to kind of determine the internal resistance of the battery. So that's what we do. I'm going to take the circuit with the battery being represented before. That's the battery and its internal resistance small r, to which we are going to connect the external resistance capital R. Of course, the current will be flowing in this direction. Now I'm going to connect an ammeter here, series, and this voltmeter in derivation. Now what we do is that we measure the PD, or the terminal PD, across R at different values of current, and we obtain a plot which will look somewhat like this. Here we have the current in ampere, and we have the voltage, or the terminal PD, in volts. Now what we find is this, that if we start here like with a very big value of current, we're not going to have so much voltage here across the resistor. But if we let this resistance be a varying resistor, and then we increase its value with time, as we increase the resistance, what we are going to notice is that the current is going to reduce in the circuit. Okay, because current is inversely proportional to resistance, and this will have a direct consequence on the voltage that is available in the circuit, in that the voltage is going to be increased, and the more we increase the resistance, the more the current is going to reduce, and the more the voltage is going to increase, and on and on. And so we're going to have a straight line like this. So if we extrapolate this line up to the 0 mark of current here, of course it will be very hard for us to evaluate the value of the voltage here, because no current is flowing here in the circuit. But theoretically, this point here is believed to be the EMF of the battery, because at this specific point we have maximum amount of voltage available in the circuit, and that can only be furnished by the battery. So incidentally also, the gradient of this line experimentally is going to give us minus R, which is nothing but the internal resistance of the battery. So this is how we can be able to determine the EMF of the battery and its internal resistance. Thank you for your kind attention.